We've already looked at vertical asymptotes and holes. If we've covered vertical, what do you think we're going to go on to next? Horizontal. Okay, horizontal. Now, there's also something we're going to see in this section called a slant asymptote, and I referred to what that was with a couple images in the very beginning the other day. I talked about these asymptotes that could be like diagonal asymptotes, like linear functions they look like. Now, we're going to have three scenarios in this section, or three scenarios here that we're going to really focus on. We're going to focus on when the numerator has a higher degree than the denominator, when it's equal to the denominator, and when it's less than the denominator. Those are the three scenarios that we're going to really be looking at here. So let's take a look at this first example here. We see we've got a function with this 6x over the quantity 3x minus 4. If we're looking at this one, what are the degrees? What are the degrees of the numerator and denominator here? Annette? 1. They're both 1. Sorry. They're both 1 in this case. Now, let's jot that down. Write down that the degree of the numerator equals the degree of the denominator. The degree of the numerator itself equals that of the denominator. Now, what we're doing here is this. We're taking a look at what's called end behavior. The behavior of the function as it goes toward the end of it. So we're saying as x gets bigger and bigger and bigger, or as x, as we see here, goes to infinity, or as x gets smaller and smaller and smaller, meaning as the graph goes to the left, what's happening? So that's the question we're asking ourselves. For example, when you're in a car and you hit a speed bump, how would you plot the function of the height of the car as a function of time? You hit a little speed bump, okay? You hit the little bump. What happens to the car over time? The next second or two, what happens?
It goes up like a little bit.
And then what happens eventually?
Back down.
And eventually just?
Goes in a straight.
So you see something like this maybe? Right? It like levels out. Maybe not that extreme, okay? But on a small scale, the shocks allow your car to oscillate at least like once or twice, very small oscillations. So I would look at this graph and say that the end behavior is that it goes toward the x-axis over time. Meaning this graph, although it starts with some oscillatory motion, as x gets bigger and bigger, meaning as I go to the right, this graph levels out and eventually sits on the x-axis. That's the end behavior. End behavior. Okay? So in this function, we're going to do the same thing now. We're going to take a look at horizontal asymptotes and how they relate to end behavior. So what we want to do here is really just make x really big. Look at the table, guys. Look at the table here, please. As x gets larger, 10, 50, 100, what's happening to the y value? It's getting closer and closer to what number?
0.
And the same thing here. Take a look. As x gets larger and larger and larger in the negative direction, it gets closer and closer to what number again? 2. Where does the 2 come from? Where do you see 2?
It's your horizontal.
But where do you see it else? Where else do you see it in a function? 6 over 3. Take a look here, please. 6 over 3. Doesn't that just give you 2? So the ratio of the leading coefficients, will tell you what the horizontal asymptote is. Let's take a look at the graph now. Here's the graph. Do you see the horizontal dashed line? That's because as x gets bigger and bigger and bigger and bigger, the value of the function starts to drop, and it gets closer and closer and closer to what number? The number is 2. And you could literally try numbers bigger than 100. Try 1,000,000. It'll just show in the calculator the answer will probably just be 2. It'll round it to be close enough to be 2. So it's never getting there, but it's getting closer and closer and closer to 2. Now, another way to approach this, here's an alternate solution. Think about it as plugging in infinity. As x gets bigger and bigger and bigger and bigger, what's a bigger and bigger and bigger number? That number or that idea is infinity. If I have 6 infinities, what does that even mean, right? 6 infinities? Because isn't infinity supposed to be the biggest number? This is what's called order of magnitude of infinities. It's a topic in like college level math you'll hear about. 6 infinities over 3 infinities. Minus 4 in the denominator. All right. you've got infinity or an infinite amount of money and you lose $4. Does that have any effect on you? You're the richest person in the world. You're Bill Gates. And you say, here's $4. At the end of the day, am I going to really care about those $4? That's really what's happening here. I've got 3 infinities, and I take away 4 from that. What is 4 to 3 infinities, right? It's like nothing. We'd say it's insignificant in math and science. Use that word. It's not to be demeaning. It sounds demeaning, I know. But in math and science, the phrase insignificant is used a lot. Okay? It's negligible. How about that word? Is that more appropriate for math and science? It's negligible. It has no effect on the problem. So in reality, what you do is you just disregard the 4. And aren't you left with just this right here? And in reality, if you think about it, 6 infinities over 3 infinities, just do math. 6 over 3. What does it just give you? 2. It's not the correct mathematical approach. Do you see why I call it an alternate approach? This is not mathematically sound. You can't really plug infinity in. But it's a way to see what happens physically. And it's very useful in the next couple examples. All right? So let's look at this next one here. We see again, look at the degrees. The degrees are the same. They're both, what are the degrees of the numerator and denominator in this case? Yeah, they're both second order. So they're both second order here. Now, there's a solution method to this besides what we said already. What's the answer right away? Just by looking at this. Y equals what? What is it going to be? The horizontal asymptote. Based on the rule we just did a minute ago. Forget even looking at the problem. Based on the simple rule, what's the answer going to be?
1/4.
1/4. We said it was the leading coefficients in the last example. 2 over 8. So the horizontal asymptote is absolutely going to be 1/4. So you can just jump right to the answer, okay? But if you want to see why it's actually true, take a look at this next approach I'm using. So the approach I'm using is saying, let me divide by the highest power in both the numerator and denominator. What was the degree we said? The degree was 2, right? So let's divide the numerator and denominator by x squared. So follow along with what I'm going to do here, please. Divide this numerator by x squared. Divide the denominator by x squared. What happens here? X squareds cancel, leaving this with just 2. And then this is 4 over x squared. 8x squared over x squared is just 8. 5x over x squared is 5 over x. Negative 3 over x squared is literally negative 3 over x squared. Now, here's where math comes into play. Here's how you have to know your number sense. Your number sense. In this problem, we're going to see that we notice here x is in the denominator. And x is getting larger and larger and larger. That's the idea of end behavior, is that x goes to infinity. It's bigger and bigger and bigger. That's what we're studying right now. If you divide by a number, and that number gets bigger and bigger and bigger, and you keep dividing by it, and you get divided by a bigger number, divide by a bigger number, what happens to the overall value of the fraction? What happens? It gets smaller. Do it, right? 1 divided by 2, 0.5. 1 divided by 3, 0.333. 1 divided by 4, 0.25. 1 divided by 5, 0.2. 1 divided by 6, 0.16 or something like that. I think it's 0.156. The idea is that as you divide by a larger number, the fraction gets smaller. So look at what happens here, please. Take a look and follow. I'm really dividing 4 by infinity here. X is getting bigger and bigger. So this is really like 4 divided by infinity. It becomes smaller and smaller. This just goes to 0. This goes to 0. This goes to 0. They all become negligible. What's your answer that you're left with no matter what here? 2 over 8. You were going to answer, George, or you were going to say something? Yeah. You're left with simply 2 over 8. Okay, so another alternate approach to seeing how you can evaluate the end behavior of a function. Divide by that highest degree. Okay, divide by that highest degree. That's what you're seeing here in the next part. Okay, we're seeing I'm putting zeros in all those spots because they are negligible. We're dividing by a bigger and bigger and bigger x value. Look at your graph here. I want to point something out. This is very interesting. Okay, this is something I didn't actually notice until I was a teacher. When I was in high school, I didn't think it was true. Remember what did I say a minute ago? Talked about asymptotes and said that the number gets closer and closer and closer, but it'll never get there, right? It'll never get to the asymptote. Well, look at this one, it did. It turns out that it crosses the asymptote for a moment here, right there, at around 2. At around x equals 2, we see that the asymptote gets crossed. And then after that, though, it gets closer and closer and closer back to the asymptote. So a horizontal, write yourself a note, a horizontal or slant asymptote can be crossed, but a vertical cannot, because it's a domain restriction. This is not a domain restriction here. See the difference? Please notice this. This is really heavy math. This is like calculus level math you're doing right now. A vertical asymptote cannot get crossed, because in the last section, vertical asymptotes cause the fraction to be undefined. It caused the entire function to have no value. So you can't cross a vertical asymptote, but you can cross a horizontal. You can. Yes, Max?
Is infinity squared bigger than infinity?
That's what I was talking about earlier with orders of magnitude of infinity, and the answer is yes, but it's not something that you're going to study in a high school math course ever. Okay? Even though you'd think like, they're both infinity though, right? Doesn't make any sense. There are orders of magnitude of infinity. Google that. Google the phrase like orders of infinity or orders of magnitude of infinity, and you can read all about it. All right, let's take a look at the next scenario. The next scenario is when the degree of the numerator is less than the degree of the denominator. So we looked at the first scenario. When the degrees are the same, we look at the ratio of the leading coefficients. In that case, it was 2/8. In the new problem now, we're looking at when the numerator has a degree that is less than the denominator. And what do you notice I do right away? I use the mathematical inappropriate way. Because it's easy. Plug infinity in for x. Literally. Plug infinity in right here. What's infinity? Take away 1.
It's just like nothing.
It's just infinity, exactly. Take away 1 from infinity, infinity is going to laugh at you and say, I've got more than you can imagine. Take away 1, it's still infinity. So literally here, this becomes just 4 over infinity. The 1 has no impact. It's negligible. So what's anything divided by infinity, though? We just said. You're dividing by a number that's getting bigger and bigger and bigger. So the overall fraction gets smaller and smaller. Why is that funny, Max?
It's like the way
Shuffling across the room with it? It gets smaller and smaller and smaller. So whenever you divide by infinity, you're just dividing by a number that's so big. Here, let me give you an example of this. Give me an example. Okay. I gave this example earlier with dividing by 0, with baseballs. I think I talked about it in this class. Sorry, my nose is killing me right now. Let's say I've got a box of baseballs and there are 40 baseballs in it. Or ping pong balls or whatever. There are 40 objects. And I decide I can take out 2 at a time. Okay, I have 2 hands. 2 at a time. There's 40 of them. How many times do I have to do it? 20 times, right? Agreed? Everybody? 2 hands, 20 times, I get them all out. Now, Max, you come over and help me. So now how many hands do we have together? We have, no, don't physically think. We have physically 4 hands together now. He's got 2 hands, I have 2 hands. So how many do we take out at a time? 4 at a time, so it takes 10 trials. Agreed? All of you come over to help me. And there's 10 of you total, right? Or 9 of you plus me makes 10, right? So now we have how many hands? 20 hands. So how many times do we have to do it? Twice. That's it, right? 20 hands. So when I'm dividing and dividing and dividing by a bigger and bigger number in the amount of hands, the answer of how many times I have to do it gets smaller and smaller. Until now you've got 40 hands. You just do it once, right? But what happens when you have more than 40 hands? You can only do it once still, right? But the idea is that if you have an infinite amount of hands, that division is getting divided by a bigger and bigger and bigger and bigger number. So theoretically, if you have 80 hands, each hand would only have to carry half of the baseball now, right? It's like the 2 hands together, each lift up half the mass. If you've got 300 hands or 1,000 hands, now each hand is only lifting a little part of it. Okay, it's the same idea as this. Actually, it's a better example. I don't know why I went to the baseball. It was the first one I thought of. You have a pizza. And Bridge is really hungry. And so is Luke. Can you guys split a pizza for anything? Or can you you still look?
Okay, let's see.
Yeah, 4 slices each, that's reasonable. But now Max shows up and Annette show up, so that's 4 of you. So instead of getting 4 slices each, you get 2 each. But then you know what? Yeehaw, and George, and Kate, and Hannah come in. There's 8 of you now, so each of you get how many slices now? 1 slice.
You're dead.
Oh, with pizza you can.
But suddenly,
you
you got even smaller. You've done when you were a kid, your parents just cut like mini slices, right? Now there's 16 of you, each get a half slice. Now it's all of Loyola sharing 1 pizza pie. What do you each get?
Like that. Like
Now it's all of New York City. You follow what I'm getting at?
Yeah.
Okay, are we there? So we understand? When you divide by infinity, the answer pretty much goes to 0. It's not 0, but it approaches 0. It's another limit. So we just drop off, or we say when anything is divided by infinity, it's 0. Even if it's negative, it's still 0. So it turns out in this problem, or in these cases, when the numerator's degree is less than the denominator, we always go to y equals 0. In the last example, the horizontal asymptote was y equals whatever the ratio of the leading coefficients were. Now the horizontal asymptote is the line y equals 0. What is that line called? We call it the, come on, just call it out. The line y equals 0 is also known as the, thank you, the horizontal axis or x-axis. Okay, horizontal axis. Okay, let's take the next example of this. Now we have an example where the numerator has a degree of 1, the denominator has a degree of 2. Again, let's take the same approach. Let's divide by the degree of the numerator. So divide both the top and bottom by x here, please. Just follow along with me as you're doing it. Okay, divide the top and bottom by x, here and here. It makes this as a result. So focus here, please, on this. Plug in x equals infinity in here now. Plug in x equals infinity. 2 over infinity, that drops off, that's just 0. Then I just left with infinity plus 4. The plus 4 does nothing because it's just 4 on top of infinity. It's still infinity. And then I'm dividing by infinity, getting 0 again. So although this was now degree numerator was equal to 1, degree of the denominator is equal to 2, in the last problem, we had the degree of the numerator equal to 0 and the degree of the denominator, equal to 0 and the degree of the denominator equal to 1 earlier. Now it's 1 and 2. But all that matters is that the numerator degree was less than the denominator. We still end up getting 0. Okay, there's our conclusion. Notice I put a conclusion at the end of each of these segments. George?
Could you just look at it and say, like...
Absolutely.
When there's no x on the top, that just equals 0?
Because the degree is less. What if there is x on the top? There's x on the top, George, right here.
Well, yeah, I mean after you divide.
Sure, sure. After you divide? Yeah, absolutely, George. But that involves dividing every time. Do you want after you do that? So just go to the first one and see that the numerator has less degree than the denominator, right? So you're done. So I equals 0. Automatic. So I'm showing you guys the derivation and the reason to these answers, but you don't have to do this every time. It's simply memorization. If the numerator is higher, leading coefficients. If the numerator are equal, leading coefficients. If the numerator is lower, y equals 0. Now we'll look at the third case when the degree of the numerator is greater than the denominator, specifically by 1. Okay, by 1. Okay. So let's look at this example here. So we've got u of x equals, and then we have a quadratic over a linear function. Quadratic over a linear. To do this, you might want a factor to start. Unfortunately, this isn't factorable. So we can go ahead and just say, you know what, let's plug infinity in, like we've done. But that doesn't help us much. Because what do I end up with? Max, here's your question, remember? I end up with infinity squared over infinity, don't I? And I think of this as like x squared over x. If I reduce, I'm left with infinity. What the heck does that tell me, right? It doesn't tell me too much. Even here, infinity squared over negative infinity leaves me with negative infinity. What does that really tell me, though? It doesn't tell me much. It just tells me that the function just goes off to infinity at the end. And at the other end, it goes off to negative infinity. So I need more specifics to this, okay? So instead, what I do is I take a look at this and I say, let me just divide the numerator by the denominator. Synthetic division tells me to plug what in?
-1.
Why?
Um,
What are you dividing by?
X plus 1, so -1 if it works to root.
Good. So I try -1, thinking, oh, I'm dividing by x plus 1. And if you go back to the actual derivation of synthetic division, it was always over x minus c, right? X minus c was divided by. So this would be really x minus -1. So you try -1 in synthetic table. Or use log division. If you want to take that root, take the extra time, use log division. But what I do is I recognize I divide this by this. When I do that, I'm left with the following. Go down to the bottom here, please. I'm left with this right here. Now, if I plug infinity in at this point in time, what happens to what I've just boxed in right here, please? Plug infinity into that, what happens to the box? Max? It becomes 0. The remainder has no effect whatsoever on the end behavior. We've used the remainder all the time, haven't we? It turns out that the remainder of -6 here, this whole piece doesn't matter. All that matters is what's left in the front. So this turns out to be what we're calling a slant asymptote. A slant asymptote. Take a look at the graph, please. We've done now vertical asymptotes in the last section. We've done 2 cases of horizontal asymptotes in this section already. We've done it with the horizontal asymptote of 0 or the leading coefficient ratio. And now we've done it with a slanted asymptote. So let's on the next slide look at our conclusions right here. And this is pretty much it. If you can remember this table, you're done. The problems are really easy. To determine if there's a horizontal or a slant asymptote, what are you pretty much looking at? The degrees. That's all you need to look at. We just went over where everything comes from, but what I want you guys to know is how to get to the answer for this. You don't have to derive everything. You don't have to divide by the highest degree or plug in infinity or do all that mess. This is what you need to do. Remember that when the degrees are equal, it's a horizontal asymptote, and it's the leading coefficients right here. When the numerator degree is less than the denominator, it's always going to be a horizontal asymptote at y equals 0. That's the x-axis. And then the third case is the one that we just looked at, when the degree of the numerator is greater than the denominator by 1 specifically, meaning it's like the degree is 3 over 2, or the degree is 4 over 3, or the degree is 2 over 1. It's got to be bigger by 1. You get y equals whatever the quotient is of either long or synthetic division, either one you want to use, and that's called a slanted asymptote. So you've got 3 types of options: horizontal 1, horizontal 2, or slant asymptote. Next. Sure? Okay. So for these examples, you have about only a couple minutes right now. But all we need to do is go through these and identify if it's horizontal or slant. Write those down first. Find them for homework on your own. Okay, on your own for homework, you can figure them out. But for now, jot down whether it's horizontal or slant just by looking at the degrees. And this is what I'm doing in my mind right now. I'm just listing the degrees so I can see later which rule applies. And notice number 5, it's a repeated. It's not an accident that that's the same as number 5 from last night. So whenever the degrees are equal, I know right away that it's horizontal, so I can go ahead and write that for these two. And whenever the numerator's degree is less than the denominator, I also know it's horizontal. So those are all horizontal right away, just by looking at the degrees. I'll figure them out, and you guys can figure them out on your own in a minute. And then we know when the degree of the numerator is greater than that, it's a slanted asymptote. And for that, we're going to use either long or synthetic division. So I'll leave it up to you to practice, because the rest is honestly just practice, right? Just come up with the numbers and figure out what they are. They're pretty easy here. The only ones that take a little while are what numbers? Yeah, the others you got. George, what's number 1? Y equals 3 over 9, which is really just 1/3. Remember, we look at the ratio of the leading coefficients there. What's number 2, Bridge? Number 2.
If you,
Just give me the answer. Y equals what?
uh,
They're all Y equals. What is it?
5 would be 0 over just 0.
Good. Just 0. They're all Y equals, right? Even the slanted ones. The third one, Hannah, the third one,
Y equals 0.
again, is just 0. Whenever the numerator is less than the denominator. And the last one, obviously, the last one. Tristan, what do you got for the last one, number 6?
For number 6,
Mm-hmm.
y equals,
Yeah. What is the coefficient there? If there's nothing shown. What's really, don't leave yet, what's really that coefficient in the denominator? If there's nothing there, what is it really? A 1. So it's 2 over 1. Okay, again, we take a look at those leading coefficients again and compare their magnitude. This is really just 2 over 1, or simply 2. So really all you have to do is numbers 4 and 5, just practice long division or synthetic. This one you need long, this one you need synthetic. Or you can use factors and see. Not much homework for this tonight at all, notice, okay? Catch up on your other classwork from your other classes.